Hi everybody and welcome back to another video. Today we're gonna talk about our nearest star. Proxima Centauri? No Bob, that is the second nearest star and is also a red dwarf. Barnard's star? No, the third nearest star. Sirius? Nope, it's the brightest star in the night sky. Come on Bob, it's the sun. See, most people, like Bob, forget what our nearest star is. Even though the sun keeps us alive and a planet from absolute disaster, we still forget about it. So today, we will talk about the sun, the only thing in the solar system we actually care about besides Mars. Let's take out our sun file. Our sun is an average star, with a radius of 696,000 kilometers, a mass of 1.99 times 10 to the power of 33 kilograms, and a surface temperature of 6,000 degrees Celsius. Way to go with big numbers. The Earth is situated around 150 million kilometers away from the Sun, the perfect distance for life. It is composed of 3 inner layers and 3 layers of the atmosphere. So yes, stars do have atmospheres and they are surprisingly handy. If you're interested in why that is, check out my other video on stars and spectra. The atmosphere of the Sun is composed of the photosphere, chromosphere, and corona. The inner workings are composed of the convection zone, radiation zone, and core, where the energy production is located. The Sun is 92.6% hydrogen, 7.3% helium, and 0.1% of other heavier elements. Hydrogen and helium are the most abundant elements in the universe, so it makes sense that they are the base of every star in the universe. It creates tons of energy via the proton-proton chain and is very active.
Climate change interruption. So, since we're talking about energy production, I thought it would only be fitting to talk about climate change. So, energy production is actually a very big problem in climate change since most of it comes from coal and oil. So, the best thing that would ever happen to us if we could create nuclear fusion. But it's very hard to reproduce. So far, we have created its nuclear counterpart, nuclear fission, which breaks down very big atoms like uranium into smaller ones. But that creates other problems like nuclear waste and other things, which also affect the environment. So, we have to create nuclear fusion, which fuses atoms together like what happens at the cores of stars. But that's the thing, cores of stars. We cannot reproduce those environments on Earth, but we have made some progress. The International Thermonuclear Experimental Reactor, or ITER, was launched in 2006 and is located in the south of France. And there, they have created their first superheated plasma and are planning to create nuclear fusion by 2023, which is pretty soon. So if they make it and we have nuclear fusion, it will really be a really great thing that happens in our fight of climate change. And as an additional bonus, a lot of people will get better access to electricity and energy.
A reasonable place to start is the photosphere. It is the surface of the sun, but isn't solid or liquid. Instead, it is gaseous and doesn't contain a strict boundary between the surface and chromosphere. The photosphere is less than 500 kilometers deep. One feature of the photosphere is a granule. They are dark-edged regions created by convection flows. After forming, they fade out the following 10 to 20 minutes. A mammoth version of a granule is a supergranule. The second atmosphere layer is the chromosphere. It lies just above the photosphere and is very thin. At the beginning of the chromosphere, the temperature is 4,500 degrees Celsius, but it rapidly increases as the atmosphere layers extend. A fantastic event happening in the chromosphere is a spicule. A spicule is a giant jet of gas extending upward from the chromosphere, lasting 5 to 15 minutes. Moving on to the corona, the last layer of the atmosphere. We record the corona and its activity with a coronagraph, a specialized telescope just for the corona. The images scientists took of the corona revealed twisted streams, hinting that the sun has a magnetic field. Boy, were they right. Mysterious evidence started piling up. For example, the temperature at the edge of the corona reaches 2 million degrees Celsius. How is that possible? So, being space detectives, NASA created a telescope, SOHO, which would observe the sun and figure out the mystery of the magnetic field. SOHO amounted to evidence of a magnetic carpet, producing far larger loops than Earth's magnetic field could imagine. Sorry, Earth. Anyhow, the magnetic field explains the hotness of the corona. The turbulence of the loops causes heat, which warms up the corona to very high temperatures. Speaking of mysteries, there was another great mystery about the sun: its composition. At the beginning of the video, when we looked at the sun's profile, I mentioned that about 93% of the sun is hydrogen and around 7% is helium, Well, this fact wasn't always known, and there were many disputes and theories about it. Bob. What is it, Bob? Please stop jumping up and down like that. Wait, you want us to meet someone? Ooh. Oh, Cecilia Payne-Gaposchkin. Thanks, Bob. Cecilia Payne-Gaposchkin, a woman astrophysicist in the 20th century, really changed our understanding of stars, including our sun, since it is a star. She invented a new way of measuring the composition of the sun, but also other stars. She could read the chemical composition of a star's atmosphere by spectral analysis of the star spectra. Not only that, but Cecilia used quantum mechanics to determine the number of atoms a star has of a particular element, leading to the 90-10% ratio. She also proved that even though some elements might not be present in the spectral lines, it does not mean they are not there. It is hiding just like information in a black hole. However, because Cecilia was a woman, her work was cut off. Other men in the institution thought it was a crazy theory, although years later, her work was appreciated and put to good use. Speaking of composition, what's the function of the convection zone, radiation zone, and core? The core is where the nuclear magic happens, where protons fuse to form a helium atom. The energy from the core is transported outwards in photons into the radiation zone, where the energy just travels through. Then the photons reach the convection zone, where convection carries energy outward to the photosphere and in space.
So we can observe all of these phenomena at home with a telescope, but you should never observe the sun without a filter for the sun or a telescope specialized for observing it. So if you want to observe this on a regular basis, then you should invest in the items I just said, or if you just want to get a sneak peek of the sun, then I'll show you a way to do it. And this is the exact same way Galileo did it in the 17th century. So just imagine for a second that this is a telescope pointing towards the sun. That is the eyepiece, and that is the objective. So instead of having your classical look at the eyepiece and see a planet situation, you take a piece of paper and you put it in front of the eyepiece. That way, the light of the sun is reflected onto the sheet of paper and not into your eyes, which will burn your retinas and render you blind. So I would say this is a much better solution. But still, you should be very careful when observing the sun not to accidentally look through the eyepiece, because it could be really, really dangerous.
The first thing you will notice on the surface of the sun are sunspots. They are large, dark areas where surface temperatures are lower than the photosphere. They are usually twice the size of Earth and disappear over a matter of weeks or months. There is a thing called the solar cycle, which lasts 11 years. In it, sunspots become more concentrated in the middle of the period and less at the beginning and end. Some other phenomena happen in the star's atmosphere, like solar flares and CMEs, which are coronal mass ejections. More about them later. Both of these occurrences happen because of the sun's magnetic field. The field is powered by the nuclear energy of the sun and has been rotating for 22 years. But the sun doesn't turn in the way you think it does. Instead, different parts of the sun rotate at varying times. For example, the equator rotates in 24.5 days, while the poles rotate in 27.8 days. And, for a weird twist, the poles of the sun reverse in the middle of the cycle. The magnetic field causes solar flares and CMEs, as I have mentioned beforehand. A prominence is ionized gas trapped in a magnetic loop that contains a lot of energy. And when two prominences coalesce, they form solar flares that can fling ionized gas and energy towards Earth's atmosphere, showering it with ionized protons. When the ionized protons are swept across the atmosphere, they can ionize the particles there, creating beautiful glowing auroras. On the other hand, CMEs aren't that harmless. If a solar flare contains enough energy, it becomes a coronal mass ejection, hence CME. Since they have a lot of energy and gas, they grow faster and with more force as they approach our atmosphere. When the CME reaches Earth's atmosphere, it hits it with radiation and ionized particles. In the process, it stops every electrically powered device from working, stopping telecommunication and the internet until the CME passes Earth. This can become very dangerous since the devices stop working indefinitely and they're very expensive to fix, especially in power plants and factories. This is why it's important to do science and to predict CMEs in advance. After this very long video, you have seen the good side of the sun and its bad side. But regardless of the sun's sometimes reckless behavior, without it, we wouldn't exist. So thanks so much for watching, and I will see you next time. Bye!